On this example, we are calculating the polar moment of inertia of a solid shaft on the left hand side, and then after we have calculated that one, we will also have to calculate what would have to be the outer diameter of this pipe to have the same polar moment of inertia. So basically having the same stiffness as the solid bar on the left. Okay, so let's start by collecting here all the equations which we are going to be needing in this task. So firstly, for shaft, so solid, the polar moment of inertia or second moment of inertia Ix is pi times d power to 4 divided by 32. Wx would be pi times d power to 3 divided by 16. For axle, for tube, the Ix is pi times. Now this is a version of this equation from the formula sheets. So you can use this version. So d on the power to 4 minus internal diameter d power to 3 so internal diameter d power to 4 in brackets divided by 32, and then the Wx for that one, the equation is pi times d power to 3 divided by 16 multiplied by 1 minus alpha power to 4, and the alpha, where the alpha is internal diameter divided by external diameter, like so. So here we have the equations for the polar moment of inertias and also the section modulus of a shaft, so solid bar, and a tube, a bar with hole in the middle. Okay, so now we can easily calculate the Ix for the shaft. So let's call it Ix S like shaft, and that one will be pi times 15 power to 4. The diameter is 15 millimeters power to 4 divided by 32, which equals to 4,970 millimeters power to 4. Okay, so now in the task we are said that okay, the tube which we are calculating here must have the same second moment of inertia. So it means that Ix T like tube has to be 4,970. So now using this formula from here, we can calculate that 4,970 has to be equal to pi times d to power 4. So we don't know the external diameter, minus 15 power to 4 divided by 32. And now when we just simply solve for the d from the equation, I'm not going to go through the steps in here. You should be capable of doing that. So when we solve for the d, the equation should be fourth root of 4,970 times 32 plus pi times 15 power to 4 millimeters power to 4 divided by pi, like so. And the answer for this one would be 17.83 millimeters. So roughly 18. So from here we can see very well that in case of when we have round solid shaft, the torsional stiffness, the polar moment of inertia, is with the shaft of diameter of 15, it is only 4,970. And the same stiffness can be achieved with a pipe that is only 3 millimeters bigger in diameter than the solid shaft. So you can understand that solid shafts are excellent in carrying torsional loads compared to solid pieces of material.